Good morning, everybody. It is Sunday morning, Hurricane Ida weekend, and if you look behind me, you will see video of what I got to go see this morning. My wife and I started out a trip this morning to the beach, checking out the wave action on the pier and the things of that nature. It looks like it's going to be a mild storm for us, and I guess history will tell whether or not I am accurate on that. But alas, you all did not come here to watch videos of the state park pier getting beat up by waves. You came here to learn some incredible new math, and with that we are going to start into solving problems involving proportional relationships. The content objective is students will solve problems involving proportional relationships. This says it's a 90-minute lesson, so it will probably take us 2 days in class to knock this one out. Good news is we don't have any new vocabulary terms to go with this lesson, so we're going to be able to skip over that and dive straight into some great new learning. In our beginning talk about it says measure the length of your hand. Can you use the information in the infographic to find the length of your forearm? And with that we have what we refer to as the golden ratio. The golden ratio, it says we use a Greek letter phi, P-H-I right here, to refer to this ratio. Around 800 years ago, a man called Leonardo Fibonacci was interested in how the rabbit population grew. He noticed that if he started with one pair of rabbits, over time the population would look like this. And you can see he had one pair of rabbits, then he had another pair of rabbits, then it went to 4, then it went to 6, then it went to, let's see here, 5 pairs, it can be 10, and so on. And it was a pattern in the birth rate or the growth of the number of rabbits he had. This pattern became known as a Fibonacci sequence. And it's something that you can find all over the place in nature. The pattern can be found by adding the two numbers before it. So 1 plus 1 is 2 that you see here. 1 plus 2 is 3 that you see here. 2 plus 3 is 5 that you see here. 3 plus 5 is 8, and so on. Your Fibonacci sequence. So get this. If you started arranging squares with the side lengths equal to the values of the Fibonacci, you will end up with what's known as the golden rectangle. What makes a golden rectangle is the dimensions reduced to the ratio of phi to 1, the golden ratio to 1. So you can see they start off with 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5, 3 plus 5 is 8, 5 plus 8 is 13, and 8 plus 13 is 21. And you notice they got a counterclockwise swirl going in. Let me take a quick picture of that and show you that swirl. So here I made a little bit bigger image, and if you see, you got a swirl that comes and starts here. 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5, 3 plus 5 is 8, 5 plus 8 is 13, and 8 plus 13 is 21. That is the swirl that we're talking about in the golden ratio. And you will recognize that, being from the beach, if y'all look at say a conch shell or a lightning whelk shell that's been cut open, you will see that exact pattern. That swirl is part of the golden ratio. We see it repeatedly in nature, in art. It's considered to be the defining property of beauty. So, what is a golden ratio, and what does it have to do with all this? Simply stated, the golden ratio written as a decimal is 1.618. There's actually a whole bunch of other digits that are involved in it, as you can see there. It's kind of like pi. It's an irrational number. It is a non-terminating, non-repeating decimal. Now we're going to examine some ratios that of some of the side lengths of the Fibonacci squares and make up a golden triangle. If you were to take 21 divided by 13, and let's look where they got this from, you have a length of 21 this way, and the 13 comes from here. So if you did the 21 divided by 13, you get the Fibonacci sequence. If you did 34 divided by 21, you get the golden ratio. If you get the 55 divided by 34, you still get the golden ratio. Each ratio is going to simplify to almost the same exact number as phi, the golden ratio. We can take and look at the length of your arm. This was our opening question. If you compared your hand to your whole forearm section to the fingertips, it's still going to be the golden ratio. Your hand is 1, and from the wrist to the elbow is going to be the 1.618. Same thing, you can calculate the measure of your forearm, just by knowing the length of your hand. So, what makes it so special? Many people believe the golden ratio makes the most pleasing and beautiful shapes. I've mentioned that before. You can see it everywhere. Here's an example of the shell that we talked about earlier. You've got the inside of a shell, and there's that spiral that I talked about. If you look in art, the way that the Mona Lisa's laid out, golden ratio. The way that the Justice or whatever building we have here is laid out, golden ratio. Even your ear is laid out in the golden ratio. We see it over and over again in nature, and it's just considered to be beautiful. I don't think ears are beautiful, though. I really don't. And with that, we are ready to actually get into our lesson. Now we're going to start off talking about proportion again. We defined a proportion in yesterday's lesson, or chapter 1, section, what was it, 5, I believe, or 8, or I don't even remember. I think it's 1, section 5. The proportion is an equation stating that two ratios or their rates are equivalent. Suppose a recipe indicates a ratio of 3 cups of milk for every 4 cups of flour. The ratio of 3 cups of milk to 4 cups of flour is an equivalent ratio to 6 cups of milk to 8 cups of flour. This ratio can be written as a proportion, and you can see that right here. What makes it a proportion? Because if we were to simplify 6 over 8 as a fraction, what would we get? 3 over 4. These are what we call equivalent ratios. They're not equal, they are equivalent. They have the same value. Equal implies that they are the same exact thing. The equal sign you see means that the ratios are equivalent. We don't say equal, as I said, we say equivalent, and the original ratio of 3 cups of milk to 4 cups of flour is maintained. The unit rate is 3/4 of a cup of milk to every 1 cup of flour. And we'll look at how they came up with that later. You can use any representation to solve a problem involving a proportional relationship. So let's select each flashcard and see different methods of finding the number of cups of milk needed if 3 cups of flour are going to be used. First off, in words, the unit rate is 3/4 of a cup of milk for every cup of flour. If you use 3/4 of a cup of flour, you need 3 times 3/4, also known as 2 1/4 cups of milk. If we wanted to use a ratio table, it would look like that. You started off with 3 cups of milk to 4 cups of water. They divided the top and bottom by 4. 3 divided by 4 is 3/4. 4 divided by 4 is 1. Remember I said I explained how they got it down to unit rate? That's how. They did it by dividing the top and bottom by your bottom number. Now they found out how many cups of cups of flour it took for 3/4 cups of milk. And we want to find out how much milk is needed for 3 cups of flour. All we have to do is multiply our unit rate by 3 on top and bottom. This is an example of showing your work. This might be one of the things you get to use in your homework tonight to justify your answers. We could also use a graph. And for a graph, you can see that, what did we had? We had, they ran it out to 4 cups of flour and 3 cups of milk. And then from there they said, okay, well, we're going to have a line from 0 to that point. Let's go backwards until we find our 3 cups of flour, and at 3 cups of flour, how much milk did we need? We needed about 2 1/4 cup. The graph is not precise, leading to my statement of about. We can't just look at that and know it's exactly 2 1/4 cups of milk at that point. And the last one, I think this is going to be, the unit rate is 3/4 cups of milk to 1 cup of flour. I showed you on the table how they found that. So your constant of proportionality is going to be 3/4. You can let y represent the number of cups of milk. You can let x represent the number of cups of flour. And right here we have a direct variation equation where y is equal to k times x. Y is equal to 3/4 times x. This is some really cool big kid math here. We're using true algebra thinking in this. Now we're going to change the x, the cups of flour, to 3. So y is equal to 3/4 times 3, which does simplify to be 2 1/4. 4 different examples of how you can say the same exact thing with math. Now let's look at how we can solve problems involving proportional relationships. The wait time on a roller coaster is 20 minutes when 160 people are in line. How long can you expect the wait time to be when 240 people are in line? Assume that this relationship is proportional. Think about this. Is your expected wait time for 240 people going to be less than, greater than, or equal to 40 minutes? Well, how are you going to calculate that? If I was to take 160 and, if I take 20 minutes and double it, I'd have 40 minutes. But if I took 160 and doubled it, then I'd be looking at 320. So 320 people could expect 40 minutes. So is 240 going to be less than, greater than, or equal to? It's going to be less than. Let's keep moving here. Now we're going to move through the slides to see how the table can be used to find your wait time of 240. We've got a ratio table set up here. You've got your time on the top. You have your number of people on the bottom. And I want you to notice that we skipped a spot here because we're going to have to go back and find a number that's better to work with. We've got 20 over 16 as our starting point, and then we have some unknown number over 240. Now there's no whole number which I can multiply 160 by to get it to be 240. So instead we're going to take and divide. And we're going to divide top and bottom by 20. The reason we picked 20 is 20 is the largest number that will divide into both 20 and 160. And when I did that, I got 1 over 8. There is a number I can multiply 8 by to get to 240, so 1 over 8 is going to work. Sometimes simplest terms won't work. Sometimes you have to look for another number that you could divide to get to and then multiply to get to your 240. But this time simplest terms is going to work. So now 8 times what number is 240? That is going to be 30. If I do it on the bottom, I have to do it on the top. 1 times 30 is 30, so what is your expected wait time going to be? Your expected wait time is going to be 30 minutes. That is showing your work, folks, where you did your loop-de-loops going back, where you do your loop-de-loops going forward. You can't just fill out the table. If you're working on the table, I need to see the loop-de-loops. I need to see what you're dividing by. I need to see what you're multiplying by to justify your answers. Now we're going to use method 2, the graph. We're going to assume that you start at point 0, 0. It is a proportional relationship, so you know that since it's a proportional relationship, you're going to start at point 0, 0. And we're going to run our graph out to what we know. We know that 20 minutes time is equal to 160, and that's going to give us this point right here. From here, we can draw a line through the 2 points, from the origin to the 20 and 160 and beyond. Because it's a proportional relationship, it's going to start at the origin and it's going to be a straight line. So from there we can keep going until we reach the point where we have 240 passengers. At that point we're going to go down, and how long should it take in time? It should take 30 minutes. This is method 2, the second good way that you can use to solve this problem. Let's look at the third way. This time they're going to use a direct variation equation. The equation represents a proportional relationship in the form y is equal to k times x, where k is your constant of proportionality, also known as your unit rate. Move through the slides here to see how to use the equation to determine the wait time for 240. First thing we need to do is find the unit rate. The unit rate is the number of people in line that is when it's expected to have a wait time of 1 minute. We're going to let y represent the number of people in line, and we're going to let x represent the number of minutes. So, hitting our next button here, you can see they start off with their formula, y is equal to k times x. Next, they plugged in what they knew. They knew the y value, the number of people in line, was 120. They knew the x value, the time, was 20 minutes. And then they isolated the variable just like I showed you in our last lesson, dividing both sides by 20. These 20s divide out, becoming 1. I would encourage you to put a 1 through there. And 1 times k is k. And over here, what are you going to put? Well, what is 160 divided by 20? That number is going to be, it is going to be 8. Give you a hint, they told you the answer right there. Check our answer. Our answer is going to check. And let's move on to our next slide. So we can say that when 8 people are in line, the expected wait is 1 minute. Now we're going to use that direct variation formula again, y equals kx, only we're going to call it y is equal to 8 times x because we established that 8 is our constant of proportionality to find out the wait time when we have 240 people in line. Hit our next button. We can take and see right here they have programmed in their formula y equals kx, k is 8, y is equal to 8 times x. From there, we have a target of 240 people. So 240 people is equal to 8 times x. We're going to isolate our variable by dividing 8 on both sides, and 240 divided by 8 is going to be the same 30 that we've been finding every other way. Circle or box your answer. So the expected wait time for 230 people is 30 minutes. Now notice you had 2 different steps to this. The first step, you had to find the constant of variation. We can see that right over, whoa, that got crazy big. We can see that right here where they solve for the constant of variation. That's step 1. After you have the constant of variation, then you plug that in for step 2 where you find the actual wait time, x's value in this case. Now there is another number way that we can look at this which we've not really talked about yet, and that would be to use a double number line. So you can set up your double number line where you have time over the number of people. You of course start at 0, 0. You draw your 2 lines, and this is what they gave us. They said that 160 people is going to take 20 minutes. Now I mentioned earlier you might not have to go all the way down to the least common denominator. So here what did they do? They divided 20 and 160 by 2, and that gave them 10 over 80. And then they multiplied 10 over 80 by 3, and that gave them what? 30 over 240. Yet another way to skin the same cat. That is going to be it for the part 1 of this lesson. When we come back for part 2, you guys are going to work this problem about Alicia making care packages on your own. See you on the next video.